I'd like to introduce our first speaker this morning, who's Jason Chuen, who you will all be quite familiar with. But just for those of you who aren't, Jason's a vascular surgeon. He's the Director of Vascular Surgery at Austin Health. He's also the Director of the Austin 3D Medical Printing Lab. So as well as being involved clinically, Jason contributes a lot to healthcare in Victoria, being advisory to a number of areas, including the Victorian Department of Health. He has a strong interest in multiculturalism, diversity and safety, and is very interested in surgical education, simulation and training, as well as other medical innovations and technology. So I'd like to invite Jason to come up and talk to us today. And he'll be talking about the use of models for pre-surgical simulation in aortic surgery.
Thank you very much, Liz. And I'll point out that the reason for my diverse list of interests is because I'm pretty much interested in everything except surgery. But as some of you may have heard this story before, the only reason I really wanted to get into 3D printing was because I just wanted to play with some toys. And I never really thought it would grow into something like this. But what it has done is it's unlocked for me the passion and the desire to create a thriving biomedical engineering community and industry in Australia. So not just Melbourne, but across the Yarra as well, and extending out as far as we can reach. So we talked yesterday about the fact that health professionals do have some slightly more restrictions than other lay people do, and I do have to make my disclosures. These organisations have funded our 3D Med Lab directly. There have been others that have assisted us indirectly, and we are still open to offers. I'll also acknowledge that the work that I'm going to talk about is not all mine. This is the work of a large team of people, and in fact even this list is not exhaustive, since we've had a number of people have come in and done small projects, and that list is far too exhaustive to show here. So one of the problems we face in aortic aneurysm surgery, and you met Gordon, who was one of my patients, is that even though we are now in an age where we can treat patients with endovascular surgery, the options are becoming greater and they're becoming more complex. The modular components, we talked about personalised surgery yesterday, and the decision making in terms of how you assemble components and personalised components to an individual patient are more and more complicated. So what we have here is our standard endovascular aneurysm repair, which consists of 3 components, a main body and 2 limbs, and 4 aneurysms that have a short sealing zone here. So we want to seal in an aneurysm here and here. Then we can extend the sealing zone up by either branching into these visceral arteries using what we call fenestrations, which are holes in a stent, or by having little branches that stick out and then go into individual branches. There are also technologies where, if you don't have the ability to custom make these devices, that you can use off-the-shelf components and assemble them in a way that achieves the same result. And there are new technologies coming out all the time to deal with challenging and difficult anatomies. The problem for us is that we have to decide which one of these options to go for, and even then, if you think you've made a decision, you're not 100% sure. So you're using your mind's eye to sort of calculate and visualise what the anatomy is going to be like. You've manipulated the devices in vitro and on the bench, and you've got some idea about how they're going to perform. You might have a bit of mathematical modelling to suggest whether it will be suitable or not.
But part of it really just comes down to gut feeling, instinct, guesswork and experience, as much as surgery is. So one of the things that we wanted to do, and I wanted to do, was to try to improve that process by having anatomical models to simulate what's going to happen in a more realistic manner. So a lot of the things that we've done have been gradually moving towards that process, and these have all been sort of little projects along the way to achieve that. The problems we do have to face, though, with any form of anatomical modelling is there are technical issues, and then there are logistic issues, and then there's, at the end of the day, the question of whether it actually does what you want it to do or not. So you have to think about things like, is your model that you're creating an accurate representation of the thing that you want to see? If it is representative of what you want to see, then how accurate is it? So are you losing some accuracy or precision in the segmentation process? Are you losing some of it in the post-processing? Are you losing some of it in the printing process? We saw the issues that arise with Darpan's work and lattice structures, and the fact that these are anisotropic materials. I use that word correctly, hopefully. And that we lose accuracy when we print, and what we print is not necessarily what we wanted. You also have to think about how the material is going to behave. So is it going to behave like normal tissue? Now, with the materials that we have limitations. So the work that Tim Hughes does is really important in terms of giving us options for materials that more closely simulate the human body. But we also, not only do we want it to behave like the human body, but we want to be able to see through it. And if you have an opaque material, then the only way to see through it is on X-ray. If you've got a clear material, then you can look through it visually on a light box or directly. But realistically, we do these operations with X-ray, so you also want to simulate that experience of looking at a screen that's disconnected from the model. And also how long it's going to last for. So is this something that you're going to destroy in the process of using it? And if you're going to destroy it, then how many of them do you need? And how practical is it to make more than one? Because if it's a quite involved process to make them, then how are you going to make that efficient and worthwhile? And at the end of the day, if what we want to do is to simulate putting stents into them, then we want to know that they are going to serve that purpose. And these principles are not unique to our project. These are principles that I think to apply to any form of anatomical modelling. So the things that we have worked on, and this is a series of cases that we used segmentation, and this was done with the Materialise Mimic software. Not that that was a blatant plug, but it is very good. And what we did was we basically segmented out some aortas, and we looked at whether we how we planned the operations without the information of this segmented model, essentially just looking at CT scans the way that we normally do, and a bit of volume rendering, versus having the ability to cut and slice and to look at these models on a computer screen. And certainly we found that a significant amount of the time it did give us extra information that altered the way that we were going to do our operations. So that was promising that there was some value in doing this. And we went the next step and printed some of these models. And for those of you who were up close, you might see that this is the model that I gave Roger yesterday, and he subsequently dressed that up. I'm not quite sure I agree with the way that he dressed it up, but it's his model and he's right to do whatever he likes with it. But these solid models we've found to be valuable both for teaching of anatomy, so helping students understand the branches of the normal aorta and the visceral arteries. These were models that we used to show patients what an aortic aneurysm was, and we did a project assessing whether or not they felt that they had been better educated through that process. This was, as I said, Roger's model. That's actually a carotid artery, so unrelated to the aortic aneurysms. And this was another model that I had used for a fenestrated graft, and this is the plan for that patient based on a Terra Recon workstation reconstruction and used to make the custom-made device. This was the 3D model that we had to visualise what was going on, and this is a volume render that we can produce on our CT workstations. So having that information I find is helpful, but that's not always going to be the case for everyone. So there may be some degree of information overload there, or there may be some incongruency in that information. And those are issues that we are yet to explore. Sometimes having more information is not always a good thing. The next step that we wanted to explore was whether or not we can not just make a solid model but a hollow model. So this is an aortic aneurysm, a thoracoabdominal aneurysm, which Andrew over here kindly segmented for us during his rotation and printed. And you'll see our MakerBot in the background, which is not the printer that printed this. It was actually a Form 2. And the black background here is actually Andrew's jacket, because we couldn't really find a photography to take a good picture. But he's done a very good job, and this model has been used to assess appearances under fluoroscopy. So this was placed under Xray, and we tried sticking wires and catheters into it from above and from below. And essentially what we found was that there were going to be some problems with this, this operation, and we used this technique to anticipate what kind of problems there would be, and at least in my mind I think that it was helpful. But again, that's an N of 1 study, and it's a proof of concept, but yet to be something to demonstrate whether it is translatable and useful for other surgeons and on a wider scale. As a proof of concept, it was very much along the line of ironing out the technical issues, and we have encountered a number of technical issues with producing these models. We are limited by the rigid materials that are available with the Form 2. There are support generation issues and support removal issues that we have to deal with, and we, like all of these additive manufacturing processes, we're iterating the way that we produce these models in order to try to make them better and more effective. One of the big problems we had was how do we actually suspend this so it doesn't fall down and break. So we put it in this, I think Jason Chuen had this fantastic idea of putting it in a bath full of water beads, which looked fantastic when we looked at it like that, but when we put it under X-ray we couldn't see a damn thing. So when we tried putting wires and clips and paper clips to try to see the model more clearly, but at the end of the day we just decided it was easier just to take it out and then stick it onto a bench directly. There have been other projects along similar lines, so in fact these publications came out after we did our work, but there are other groups who are working on printing rigid models using a variety of materials and then looking at them under a light box. In this circumstance, I think we're the only ones that actually put it under X-ray. There is a company, Vascutech Terumo, who when they provide their custom-made grafts, they do print a short segment of aorta, just a visceral segment, to test deployment. And again, it's challenged by the fact that this is a rigid material, and what they don't simulate is the entire aorta, so that we can assess things like cannulation and negotiation. There's other applications in terms of intraoperative use, so we've talked about surgical guides, and in those locations where a custom-made graft is not available, then you can use these to build custom-made grafts on the table. And what we're hoping to see, and what we're already seeing, is this growth in publications in the vascular surgery space. So at the end of the day, this is very much a work in progress, and with each month that goes by, we seem to find more ideas and more ways to improve this process, and also hopefully once we've got it down pat, then we'll assess it much more rigorously. But for the moment, my registrars are really very excited that they get to play with the toys that I wanted in the first place. So thank you very much.